Moving right along in our units about logarithms, today we are going to work on figuring out when our antiderivative will have a natural log show up, working on solving indefinite and definite integrals where those logarithms show up. So please note, we're not going to take the antiderivative of a logarithm. That's not something we study in a Calculus 1 class, but we will study integrals who turn into the natural log, right? So integrals that yield natural log. Remember what the power rule for integrals states. If we take the antiderivative of x to the n with respect to x, we increase the power by 1, divide by that new power, and then we have our constant of integration because this was an indefinite integral. Well, just like Superman's powers are deprived when kryptonite is present, so does the power rule for integrals. What is the one time that we cannot use the power rule? Hopefully you're saying when n is equal to -1. The reason for that is if I take the antiderivative of x to the negative first dx and I try to apply the power rule, I would end up with x to the 0 divided by 0 plus c, and this can't happen. So our power rule, n can never be equal to -1. So there's got to be something that still allows us to find the antiderivative when that power rule is rendered useless. So Mr. Lakin was going to write a Desmos activity, but we decided to go a little more straightforward based on recent Desmos history. All right. So we've got some examples. Yes, there are 15 of them. Yes, we are going to do all of them. Yes, they will help in your understanding. So we're going to have some derivatives, some antiderivatives, and we'll get some patterns going on here. We take the derivative with respect to x of the natural log of x. Remember, it's going to be 1 over the argument times the derivative of the argument, which is really just equal to 1 over x. And now you might be looking at this one and saying, Ms. Schwartz, it's literally the same problem, and you are right. It was cut and pasted. Well, Control-C, Control-V. Take the derivative with respect to x of the natural log of an argument is 1 over the argument times the derivative of the argument, which again is equal to 1 over x. And the reason we do this is now we want to get into this antiderivative of 1 over x. Well, this is a problem because this is the antiderivative of x to the negative first, and so we know our power rule won't work. But if we think back to this idea of an antiderivative asks the question, what did I take the derivative of that led me to this moment? Well, I took the derivative of the natural log of x with some constant. Right? And you can check that by taking the derivative. Well, what happens if I take the derivative of the natural log? I get right back to 1 over x. The only thing we want to make sure that we include is an absolute value around that x. And the reason for that is we know that the domain of the natural log has to be positive x values, right? We have to have a positive argument. Also, it gets to that idea of we've always said that the derivative of the natural log of x is 1 over x if x was greater than 0. So by putting these absolute value bars on, we're guaranteeing that our argument is actually positive. All right, so in thinking about this, I like to view, numbers on a number line. So if I have a number line that represents x to the nth, everywhere along that number line, negative numbers, 0, positive numbers, everywhere along that number line, I get to use the power rule. Except at this one moment, when we have x to the negative first, that moves to the natural log of x for the antiderivative. So any other number on our number line, you can use the power rule if you have that n in the exponent. Except -1, it turns into the natural log of the absolute value. All right. I'm going to make these a little bit bigger for us, so I have a little more room to write. We got lots of examples. Thank you, Mr. Lakin. So the first one, take the derivative of the natural log of x squared. Well, we know that we can do this a couple different ways. We can just say, okay, it's 1 over the argument times the derivative of the argument. So we get 2 over x. The other way we could have done that, remember, is to use log properties before we take the derivative. So swing that 2 down in front. That derivative then is 2 times 1 over x, which again gets us 2 over x. All right, well, the next one, take the derivative of 4 plus the natural log of x squared. The derivative of 4 is 0, and we just did. The derivative of the natural log of x squared is 2 over x, which means we end up with 2 over x. Well, now then, if I'm taking the antiderivative of 2 over x, I can view that as 2 times the integral of 1 over x dx, which means I get 2 natural log of the absolute value of x plus c. Now, the last thing would be that your textbook and some multiple choice answers will put this x squared. They'll move the 2 up using your log properties, just like I moved the 2 down before I took the derivative. Okay? But still, we turn into the natural log when we have that x to the negative first in the denominator. All right, building a little bit more. We've got 2 more derivatives that lead us to an integral. Pattern building again. So here, before I get started, I could do 1 over the argument times the derivative of the argument. But the derivative of this argument is going to get a little bit messy and have some negative exponents in it that I might not want to deal with. So instead, I'm going to use those log properties. The cubed root of x is the same thing as x to the 1/3. So I'm going to swing that 1/3 down in front. This will be the natural log of x then. Again, haven't done calculus, just using my pre-calc knowledge. So then when I take the derivative, I get 1/3 times 1 over x, which would really be the same thing as 1 over 3x. This next one then, again, I could say 1 over the argument times the derivative of that argument, but that argument's derivative is going to have some negative exponents in it that I don't really care to deal with. So I'm going to rewrite again using properties of logarithms, not calculus. No calculus has been done yet. Now, when I take the derivative of 1/2 natural log of x, the 1/2 hangs out in front as a constant. The derivative of the natural log of x is 1 over x. So this derivative overall is 1 over 2x. All right, well then let's think about this antiderivative. We have the antiderivative of 1 over 4x. I can take out a 1/4. So now when I take the antiderivative, I get 1/4 the natural log of the absolute value of x plus c. And then the final result could be written as the 4th root of x plus c. And in this case, you can leave the absolute value bars, but the 4th root is going to make that a positive input. Just like up here, I could have dropped the absolute value bars because squaring the x is going to make that positive. The thing is, though, you're safe with the absolute value bars, right? Because let's say you had a positive number and you took the absolute value. Okay, you stay positive. But on the off chance that we have a negative number, if you forget those absolute value bars, we've got a problem. So you're safest to keep those absolute value bars on. We'll have a couple of examples when we get to differential equations, where we talk about when do we really need to drop those absolute values, or when could we drop those absolute values. All right, example 10 of 15. We're getting there. Take the derivative of the natural log of x plus 4. Well, that's going to be 1 over the argument times the derivative of the argument, which is really just 1 over x plus 4. So then number 11 says take the antiderivative of 1 over x plus 4. And you're probably saying, well, yeah, Ms. Schwartz, we just did the derivative. So now we take the antiderivative. It goes right back to where we started. Hopefully you remember that we have a plus c. So natural log of the absolute value of x plus 4 plus c. But let's talk about what really needs to go on here. Okay? What really needs to happen is we need to do a u substitution. Because this 1 over x plus 4 does not fit our base rule of 1 over x dx, right? Those were perfect variable matches. So here I've got x plus 4 with a dx, so I'm going to need to do a u sub. U equals x plus 4, du equals dx. So when I do my substitutions, I'm going to end up with the integral of 1 over u, and then du and dx are a perfect match. So then this ends up being the natural log of the absolute value of u plus c, and then I can sub in that u value. Okay, and the reason why this is important is that when we're integrating a rational function, okay, when we have a denominator that has a function in it, most of the time you're going to pick that as your u. And we're going to end up using u substitution to help deal with that integral because we have a whole function in the denominator as opposed to just the variable of integration of just x, right? This one has x plus 4. So let's use that same logic in example 12. I'm going to let u be equal to x plus 4. Du then is equal to dx. So when I go through and I replace this integral, I'm going to have 1 over u squared, because I still have that square on there. And then my dx is, again, a perfect replacement with du. This one, though, this is the same thing now as taking the antiderivative of u to the negative second du. And that just becomes add 1 and divide by the new power. Because remember, negative 2 is right here on the number line. That's not a problem for me, right? I can take the antiderivative of that using the power rule. It's only when when the n is negative 1 as your exponent that we have to use that natural log rule. So this one, Mr. Lakin, being sneaky, we're just going to use the power rule. So taking the antiderivative of u to the negative second becomes u to the negative first over negative 1 plus c. Go through and replace your u. You'll get x plus 4 to the negative first over negative 1 plus c. And then if you wanted to clean that up, we have the negative 1, right, in the numerator, and x plus 4 moves to the denominator. Okay, and you can always check your answer, of course, by taking the derivative. This one, when you take the derivative of natural log, we end up with 1 over. This one, when you take the derivative, you would swing the power down and lower that to negative 2, which is what we have right there. So before we do the last 3 problems, we're going to do those together in class. Explain to your neighbor, or think for yourself if you're not talking to somebody right now, when will your antiderivative have the natural logarithm? So my hint to you is remembering this whole number line of infinite numbers, 0, 1, 2, 3, 4, negative 1, 2, 3, 4. I can use the power rule. Any number for x to the n, except when n equals negative 1, that becomes the natural log of the absolute value plus c. Okay? So power rule being x to the n plus 1 over n plus 1 plus c. Think about how you can write that. Think about how you're going to remember that for yourself. And then we will work on problems 13, 14, and 15. They have a little bit more complex division going on. We'll work on those together when you come back to class.